So we said that when we deal with the problem of optimization, mean or max, we had to optimize a function over a set S. So today we will focus on the function S, on the function F. So the properties, okay. So it's we are minimizing real values. So we are dealing with real functions, but not defined on R, but on Rn. Okay, so the definition. So we are interested in functions that are defined on a set S or a domain. Let's say now we are dealing that is a subset of Rn and taking values fx, that is f of x1 xn, that is a real number. Okay, so df as usual is the domain. This is the domain of f. So it's important to know the first thing, the domain where f, your function, is defined. The second, of course, studying functions, the purpose is to know the function completely. The last step of knowing function is to visualize the function, that is, knowing the graph of the function. This is the last step. So for function of one variable, we know how all the steps we have to go through to that we can graph it. For functions of several variables, it is hard to visualize function of several variables manually. We use softwares to have a big picture of the function. Still we can do it for n equal 1. So if you have a function of one variable, okay, n equal 2, then you are plotting z. We plot fxy, that is the graph here. So let's remind ourselves here. The graph here is the set of the point x fx. You remember, when your x is in the domain, describes the domain. If we define, so for this situation, when we are in dimension 2, we will plot the point x, y, and z, which is fxy. You see, so there's our points in space x, y, z. So when x, y describe the domain. Okay, so you see how it is complex. It's not easy to have just manually guess the shape of the graph. For n greater than 2, so greater or equal 3, not possible to visualize. No, not possible to visualize. Okay, to visualize the graph of, you can consider the definition, of course, characterize the set, but visualizing is no more possible for our perception. Okay, now it is good to identify some sets of graphs of function. Okay, yes, it is, yes. So how the idea to visualize the graph of function is we use level curves. Okay, the method, so is using, so either graphing using softwares, and we have the surface, etc., but the principle is to use level curves. So how the answer is use level curves. Okay, level curves. So we can imagine if my graph is included in R3, then I am working in space. Okay, so suppose that I have the graph of my function is half of the sphere. Okay, if it is the half of the sphere, so I can imagine plans. I can imagine set parallel plans cutting, so set at several levels. Okay, if I can, so graph at level z1, z2, etc., and look at the Z3, etc., and look at the intersection. So the intersection will be in this plane, for example, in this set I will have a trace of my, okay, so in plane, in some plane, okay, I will have the intersection will have a shape like that, and repeat, this is at level Z equal ZK. Okay, so suppose you increase your planes, then you use the projection in the plane, then plot this in the plane XY. Okay, here is the plane, here the plane, if you remember, here the plane XY. So here I plotted it like that, vertically. Okay, and then report there's traces, okay, and we can even some softwares we can locate the value of the level curves at which level we took. So if you regroup all your you see your traces, you will get then you will have an idea of the shape of your, okay, we can have an idea. Etc. You see, that means we can reconstruct the, okay, we can elevate each level curve to its corresponding level and regroup again, reconstruct our shape. Okay, so this is a way how to use level curves to graph a function of two variables. Some of them you can, yes, you can have, it is good to know some of them. Examples. So you have paraboloid. So paraboloid is general equation is x2 over a2 plus y2 over z2. Okay. Sphere here, the sphere you see here, the sphere we said or ellipsoid, or just the sphere is, yes, is half of an ellipsoid. So ellipsoid, so this is a set of general equation, so it's not the graph of a function, but we can deduce part of it as we can look at it. Okay, b2 plus z2 over c2 equal 1. Those are the standard equations. Okay, and you can look at the notes, you will see how we can identify the sets. Okay, there is the cone also. The cone is more z square is equal x2 over e2 plus b2 y2 over b2, and there is variant if you move the change the role of x and y and z, etc. Okay, so you can have a look and practice on the graph of the sets. And ellipsoids, mainly there's three, you need to know how they work. Okay, so just have an idea here. For example, the suitable traces you can use, okay, on the plan and the traces. Just with few plans you can have an idea on the shape. Okay, so for a cone, you can use the following traces. For the ellipse, so for the ellipse also, ellipsoid, the plan, and the traces, and here a plan of the trace. Okay, so let's do it for the cone. For the cone, you choose z equals 0, so the intersection will give you the point 0, 0. Okay, so you have okay, with the plan y equals 0, you will have z equal plus or minus x over a. So you have lines. With x equals 0 also you will have lines, z equal plus or minus y over b. And finally, if you take z equal plus or minus 1, you will have z equal x2 over a2 plus ellipses. Okay, so you will have something like that. Z equal 1, at this you have this level 1, you will have then an ellipse, okay, equal 1. That is, you move with a distance on direction x, with y distance you move with b, let's say b, okay. Then you join, you can join the points. You will have points here and an opposite one, and join your points like that. Okay, and z, this is level z equal 1, that you do the same at z equal minus 1. Okay, and you have these two ellipses, and you join this with the lines. Okay, you will have similar, and you have the shape of your cone. Okay, so this is how it works. Okay, there is point here also, you have another line with the other side. Okay, this is for the cone. For the ellipsoid, with the ellipsoid, we choose the following plans: z equals 0, so that we have then an ellipse on the plane. Okay, so here it is. Let's start from the beginning: x, y, and z. So I have the trace A, let's say B, and then it's for an ellipse you need just the vertices of your ellipse. Okay, so you have 4 points and you join them and you get your trace. Okay, trace. Then you choose y equals 0, so the plane y equals 0 in the plane xz. You look at your intersection of your set of points with y equals 0, which is the equation of the plane xz. So you will have an ellipse again, x2 over a2 plus z2 over c2 equal 1. So you will have distance c here. You will have a point that there's plus there's 2 points and the other one, and you will get the trace. Okay, like that. And then the last one, when you take x equals 0, you will have another y2 plus over b2 plus z2 or c2 equal 1. So we can join these points. Okay, and like that, you see, you get the global shape of your ellipse. And the last set we may have along is the paraboloid. It's good to identify your function, the graph of your function. It gives you an idea on your set, how your function is behaving, taking large values or not. You see, for example, here my function, if I'm, yes, on ellipsoid, so yes, it will be bounded. Okay, yes, so we said paraboloid, z equals 0 first, you will have 0 0, so it is part of the graph. This okay, x y, so it's part of the graph. The origin is part of the graph. Then you take z equal 1, you will get an ellipse, y2 plus y2 over b2, sorry, here b2 equal 1. So you will have an ellipse here, so distance if in the direction of x minus a. Okay, you see a minus a. Then in the direction b, use yb, you will have b and minus b. So you have 4 points for your ellipse at the level z equal 1. This is 1. So you join your 2 points and you get your ellipse here. Okay, and then the last one, you take x equals 0, you get a paraboloid y2 over b2 in the plane. So this is x equals 0, so that means you are working in the plane yz, and you will have, then it's enough to join those 2 points. They are part of the curve, the set. Okay, and the last one, yes, the last one, will be joining this the parabola in the plane xz. You join this points. Okay, so this is for y equals 0. You have the point x. Okay, for y equals 0 you have z equal x2 over a2. Okay, so this is how, of course, your set continues. This is just the trace at level z equal 1, but the parabola are continuing, and definitely here also, and you will have more ellipses, ellipsoid, ellipse traces every level z positive. There is no point for z negative. It's not part of the paraboloid. Okay, but the global shape will be something like that, bigger than we are looking at. So this is about the three categories you should be able to identify from their general equation, and gives you information. There are other concerns. You need to know properties for functions of several variables, limit behaviors, but we will not limits. Okay, limits continuity. The definitions are still the same, but just manipulating definition is more complex. Okay, so we will say limit of a function of x, y, two variables, which you can, or just let's say larger, yes, since we define the distance for r in Rn. X approaching x0 equal a number L belonging to R is here. If and only if for any epsilon positive we can find an R positive or delta positive, such that each time x is close to x0 norm, in terms of norm, then then the norm or the absolute value here fx minus the number L is less than epsilon. So we need to, for continuity, for continuity we add L equal fx0. We need that, for continuity. There is the other property also is differentiability. So before that we define something closer, partial derivative. So this is the definition, uses the concept of limit. So it's we fix let's say we fix the other variables. So fx0 at y, f at x0. So let's give the general definition. So we fix if I want the derivative for the first variable with respect of xi, so it will be the limit of the variation of my function. So it will say x0 1 up to x0 I plus h. And let's continue then, x0 I plus 1 and x0 n minus f at x0 over h as h approaches 0. So it will be the limit of so it will be this is the definition. So this is our definition about the limit. So we freeze other variables and we let one of them changing. So we define this partial derivative. There is a vector that we call gradient vector. That is important. We form the gradient of f. Gradient of f is at point x0 is we regroup all the vectors or the components of the partial difference. At x0, fx partial derivative with second variable x at x0 applied at x0. So it will be involved in our calculation later. Otherwise, there are of course the differentiability. Now the meaning of differentiability is extended to functions of several variables. So it is ability, okay, differentiability. So it is extended. We will say that f is differentiable at x0, f is differentiable at point x0 if and only if we can write fx. Okay, fx is like fx0 closed, so it has a linear part, okay, plus, so there is a derivative. So these vector gradients sometimes we denote it just f prime at x0. So let's keep the notation f prime at x0. Dot here, this is the vector, so there is a dot product here that it involves x minus x0 plus a function plus, let's say, something in the norm of x minus x0 and epsilon of, let's x, okay, with epsilon, limit of epsilon x is 0 as x approaches x0. Okay, so this is when this writing is satisfied, we can say that f is differentiable. A situation that is we are sure that that it is true is given by the following theorem. If fxi exists and are continuous continuous for I from 1 up to n, then so if then f is differentiable. Okay, so if at x0, okay, at the point x0, then f is differentiable at x0. Okay, so this is, it's much easier to check the differentiability than using finding a function epsilon, etc. So this is the situation what you have. Of course, there are other theorems, but it's not important to know them. We will talk about them when we need them to check a result. And it's not the purpose of the course to know all these similar chain rule formula, Clairaut's theorem. This is all the content of the course of second year calculus. But we will just use them as tool or refer to these theorems and show how we can apply them. But the more important thing is to be able to identify some graphs of particular functions like this ones here. The sets of points, it's good to know them, to get familiar with them. Yes, the gradient vector, we will need it, and understand globally what is required about differentiability of function of several variables. So, okay, so visualizing some graph sets in space. Okay, this is the most important.